Hello everyone. In the previous lecture, I had mentioned that I would be taking up an example. So here it is. We are considering a very thin beam or column or bar, rod, whatever you want to call it, uh, in this fashion. And it may look that there is something very special going on at the top, but I mean, it's really nothing. It's just a hinged end. Uh, except that it is so arranged that this hinged end uh, is free to slide along like this, okay, in the vertical direction. uh, on the other hand, this hinged end, so that support itself uh, is attached to a certain wall or ground, okay, as you want to understand it. Anyway, so what is going to happen is that when we apply a vertically downward load, a force like this, then it is of course going to uh, compress, and because we have these kinds of rollers here, it can actually compress, okay. uh, Now, we know from our physical understanding or intuition, or maybe from our undergraduate knowledge, that beyond a certain value of this force, let's say this is P, it is going to buckle. This slender rod is going to buckle. Okay, but we want to address this buckling in a systematic fashion based on the theory that we have been developing. So let us take a look back at the equations that we arrived at in the previous video. So these are the set of equations. What I'll do is I'll just copy paste this set of equations and see how we may specialize this general set of equations to the specific case at hand. Okay. All right. So I have my set of equations here. Okay, so the objective here is clear, that we want to find out the value of the critical force P, okay, which will induce buckling. And in the process, we want to get some insights into the deflection, because you see the governing equation that we have here, that certainly involves the variable P, but it is an equation, it is a differential equation in terms of the deflection W. So let us see what insights we can obtain about the W also. Okay, so our immediate job now is to understand the specific boundary conditions which will be applicable given this kind of a physical setup. Okay, so what we'll do is, first of all, we'll set up our coordinate axis. So let's say we have our x vertically upward here and z like this, okay, uh, which means that our y will be pointing out of the plane of the screen, but I'm not going to draw that here, just to avoid any clutter. So you understand that the deflection W, that is taking place along the z direction, okay, and all the axial compression, that is going to take place along this x direction, or specifically along the negative x direction. But of course, you note that in the way that we have found out or reduced our set of equations, that stretching variable us has disappeared. Okay, so I suggest that if these terms, the stretching variable and such other things, are not very familiar to you, you please take a look at the previous video. All right, now uh, as I was saying, our first job at hand is to specialize our boundary conditions given this physical setup. So uh, we have these boundary conditions at x equal to 0 and at x equal to L, we have these things. So you first of all note that at x equal to 0, okay, at x equal to 0, what is specified? Okay, if at all anything. At x equal to 0, we know for a fact that this W is very much specified, because uh, it is constrained against moving in the z direction. So W is equal to 0. Okay. Similarly, at x equal to L, okay, at the other end, the W is again 0. Please do not confuse with the fact that US is not specified. Okay, that is true that US is not specified. The stretching variable is not specified because this end can actually move down. So we don't know how much it will move down. But W is in the Z direction. So W is not is very much specified. Okay, it is constrained against moving in this Z direction at x equal to L. So one thing we are sure is that this is true. W is specified. Okay, so this double tick mark, you can kind of understand it that one tick mark for x equal to 0 and the other tick mark for x equal to L. What about the other set of boundary conditions? You see, again, both these ends are hinged ends. Okay, uh, hinged ends means there is no resistance against the rotation of this end. There is no resistance against the rotation at this end. And since there is no resistance against the rotation, we do not know anything a priori about the slope that this beam or the rod can take. Okay, since that rotation is not resisted, we do not know a priori what the slope will be. Okay, so suppose instead of this hinged end, this was a clamped end. Okay, so a clamped end would I mean the implication of a clamped end is that the rotation is completely prevented, which means that the slope is fixed. Okay, so that is not the case here. So this dw dx, which represents the slope, that is certainly not specified, and that is true at x equal to 0 as well as at x equal to L. So because this is not specified, it is the other condition, the either or. Okay, so it is always this sort of a toss up between the either and or. If one of them is not specified, the other must be true. So here we have ei d square w dx square is equal to 0, and again we will put two tick marks here to represent the fact that this is true at x equal to 0 and at x equal to L. So in totality, what we have is this. For our governing differential equation, we have this equation. There is no doubt about it. You have only one equation. And please note that this is a fourth order ordinary differential equation. Okay. And because it is a fourth order ordinary differential equation, we will need four conditions to solve it. And those four conditions will be given by the two conditions at x equal to 0, this, and the two conditions at x equal to L, this and this. Okay, so that's all that we have to do. So this physical problem or this mechanical problem that we have in our hand, that has now been reduced to just solving this differential equation subject to this boundary conditions. Okay, and the moment we can do that, we are very happy because we have all been trained in first year engineering mathematics. So we can proceed. Let us do that. Okay, and see what happens. All right. So first of all, we have to deal with this equation, and to solve this equation, I mean, you can have different methods, but what we are going to do is, uh, uh, so first of all, what I'll do is I'll just rewrite this equation in a slightly different form. Okay. So let me write this in this form. I will divide throughout by this EI so that I end up with this. Furthermore, you note that for our problem, this Q is equal to 0. I do not have the presence of any lateral load. Okay, you understand that this was copy pasted from the general theory, just like the boundary conditions were copy pasted. So for the specific case at hand, Q is equal to 0. So I don't have to worry about the right hand side, that is just 0. Okay, now what we do is usually this P by EI, you note that this P is a positive thing, this E is positive, I is positive, so this entire thing is positive. So what we'll do is we will just write this particular combination as K square. The K square denotes that this particular combination is positive no matter what the value of K may be. Okay. If you wanted, you could have written this simply as k and just said that has to be positive. But the way that we are going to end up with the solution, it's just the answer shows up in a nicer fashion if we start out with this k square, and you will see why. Okay. Uh, Now we have to solve this. So to solve this, what we do is we assume a solution form. We assume a solution form which is W is equal to e to the power mx. The motivation for taking this e to the power mx form, where m is something unknown yet we have to solve for it, is that you see that I mean this kinds of derivatives. Okay, so if you operate this derivatives on this thing, it will keep on giving up multiples of m. So if you differentiate once, you'll get m, m square, m cube, m4, all those things. But the heart and soul of this, the way that this depends on x, that remains unchanged. Okay, and that has certain benefits in the way that the solution can be attacked. Okay, so let us not get too much into the mathematical theory behind that, and let us try to solve this thing. Okay, so let me go to the next page. If I substitute this w is equal to e to the power mx form here, what am I going to get? So this thing, m4 m to the power 4 plus k square m square is equal to 0. You note what has happened is that I'm also getting this e to the power mx here and e to the power mx here, that I have just cancelled out. Okay, so now this can be written like this, and now you see that it's quite easy to write down the solution. What we will obtain is that this it is this m square equal to 0 or m square plus k square equal to 0. Those two conditions will give us the 0 values for this. So what we are going to end up with is this 0 0. We make it a point to write this 0 twice to actually explicitly show that 0 is indeed a repeated root, and that will have some consequence in the way that the solution shapes up. For the roots from this m square plus k square equal to 0 part, what we are going to have is plus minus I k. Okay, where you note this I is the familiar square root of minus 1. Okay. So I hope nobody will have any problem with this. So given that we have ended up with this m, how can we write the w? Okay, so we have 4 roots here. So uh, let's write, so let's use different coefficients for each of these uh, choices of m. Okay, so first of all, for this repeated root 0 0, I have to write this as cx plus d. Okay, so if you're not sure what has gone on there, you need to revise your first year engineering mathematics. So suppose this were not m square, this were just m. Okay, and then it was m times m square plus k square. So what you would have obtained is m equal to 0. In that case, all that you have to do is to just think that this is like some c into e to the power 0x, and that is just c. Okay, so we would not have anything like this. But it is also wrong to think that this would be, because these are 0 and 0, it will be like c e to the power 0x plus d e to the power 0x. That would be wrong. Okay, so to know more about the theory, you really need to revise the first year engineering mathematics. Okay, regarding the other part, this plus minus ik, you note that I have written this as a dash and b dash, just to prepare myself for the fact that I would like to rewrite this thing not in terms of this exponentials, rather in terms of cos and sine. Okay, so what I'm going to do is this e to the power ik, that I'm going to write as cos k plus I sine k, and this as cos k minus I sine k, and then I'm going to combine those cos terms and the sine terms, and ultimately what I'm going to obtain is something like this. Please note that I have missed the x here. Okay, that should be written. So this is a cos x, cos kx plus b sine kx plus cx plus d. So that's my solution for w. All right, so now all that I have to do is to utilize my boundary conditions one by one. So let me just take a quick look at what the boundary conditions are. At x equal to 0 and at x equal to L, I have the w is specified, and indeed this w is specified is actually that this w is actually 0. Okay, so this is only for the special case that we have here. Another condition is that this ei on double derivative of w with respect to x, that is equal to 0. Okay, so now the boundary conditions. At x equal to 0, w is equal to 0. That implies if I substitute x equal to 0 here, this just gives me a, this vanishes, this also vanishes, and I am left with this. All right, next, at x equal to L, w equal to 0. That gives me a cos kl plus b sin kl plus cl plus d equal to 0. Okay, there is not much that I can do here, except, I mean, one can argue that this d can be substituted by minus a, but right now that doesn't really do me any good. Okay, so we'll come back to it. Next, at x equal to 0. Okay, now please note that once we have this, let's just find out the expression for d squared w dx squared. And please note that I'll be doing this at one shot, not okay. So I'll skip a step. So what I'm going to get here is minus a square a cos kx and minus k square b sin kx. All right. So at x equal to 0, what I have to use is ei d square w dx square is equal to 0, and that is going to give me, if I just substitute x equal to 0 here, I don't have to bother about this ei because the right hand side is 0. So this is just going to give me minus k square a. So this is just giving me 1 cos kl cos k0 is 1, and this is just going to give me 0. The whole term is 0 because sin k is 0. Okay, so this is 0, which implies that a is equal to 0. Now the moment we have a equal to 0, we can go back here and say that d is equal to minus a is also equal to 0. Okay, next, at x equal to L, I again have the condition that ei d square w dx square is equal to 0. So what that gives me, I have already found out that a is 0 and d is 0. So here you see what I'm getting from this thing is that minus k square a cos kl minus k square b sin kl, but really, I mean, this a is 0, so we don't have to worry. So ultimately what we are obtaining from here is this thing, that b sin KL is equal to 0. Okay, now uh, if you just go back here and see that this A is 0, this D is 0, and we have just found out that B sine KL is equal to 0, which means that CL is equal to minus B sine KL, which implies that C is equal to 0. Okay, now if we come back to this equation, B sine KL equal to 0, and we think that this equation is going to be solved or is going to be satisfied if we take B equal to 0, then what we are basically ending up with, if you just look at this expression for W, is that A is 0, B is 0, C is 0, and D is 0, so W is 0. So this is not a very interesting solution. We say in mathematical terms that this is a trivial solution. So of course, if you have that kind of an equation, W is equal to 0 is a solution, but that's not very interesting. Especially not interesting because we are looking to find or investigate the possibility of buckling. Okay, so we really need to find a solution for W which would be non-zero. Okay, so what I mean to say is here that if you look at this diagram, then the buckling would have, we would say that buckling is indeed occurring if there is a non-zero deflection in this z direction. So it really does us no good if we end up with a solution which says that W is always equal to 0. That is, there is no deflection along the z direction. That is not at all what we are looking for if we are interested to study buckling. Okay, so the question arises that, okay, that is a certain possibility even though it is not interesting, but is there any possibility? Okay, that is the key question to ask. Is there any possibility that even if uh, uh, we have this kind of a thing, there may be another alternative solution where W may not be 0? Does that solution exist? Okay, so if that solution exists, then the only possibility in our hand is to claim that B is not equal to 0. Okay, so the only possibility, the only chance we have left for W not to be equal to 0 identically is for B not to be equal to 0. But this particular entire combination B sine KL has to be equal to 0, that we have found out mathematically. So the situation is like this particular combination is equal to 0, B itself should not be 0. If we indeed have to end up with buckling, that means sine KL has to be 0. Okay, so it is through that argument we say that sine KL equal to 0 for non-trivial solution. Sometimes in textbooks it is written in very short for non-trivial solutions the sine KL equal to 0, but you should always try to connect that kind of a mathematical statement, non-trivial solution, with what you are actually looking for mechanically in the problem at hand. We are looking for possibilities of buckling, the mechanical phenomenon, and that will be possible only and only if this B is not equal to 0, and which leaves us with the only possibility that sine KL must be equal to 0. Okay, so how is this possible? When is sine KL equal to 0? So sine KL will be equal to 0 if KL takes on values which are multiples of pi. So you understand that this n must be from the set of integers. Okay, but you note that this I mean we have taken uh, our k square is positive, so there is no guarantee that k has to be positive or negative. But if one were to think that k also is positive, then you have to really mention that n must be from the set of positive integers. So otherwise, if you allow for the fact that k may be negative, then there is no such restriction on this. But it is important to note that this is not the set of natural numbers, it is the set of it is a set of integers, okay, so including 0, because you see that if you take KL equal to 0, that also is a possibility, okay. So that's just mathematical speak, but let's see just what happens, okay. So what is this K? Okay, so let me go to the next page and continue the discussion. We have arrived at this KL is equal to n pi. K, if you remember, okay, so K, uh, this K square is equal to P by EI. Okay, so what we are going to do is to take the square of this. Now K square is P by EI. I take the L square to the other side, so that P is equal to n square pi square EI by L square. Now, this answer that we have obtained, it is a very important and classical result from mechanics of solids. Uh, what this is saying is that for buckling to occur, the force P, the compressive force P, when it takes this kinds of critical values, you see this pi square is just a constant. The Young's modulus is a constant parameter for a given physical setup. The I is just dependent on the geometry of the cross section. The L is also dependent on the geometry of the rod. It's just the length of the rod. So it is this crucial factor here is this n. Okay, so if we take n equal to 1, 2, various things, then what is going to happen is that for values like pi square EI by L square, then 4 pi square EI by L square, those specific values, our theory is predicting that buckling should occur. Buckling should occur means that you are going to end up with non-zero solutions of W. Okay, so for these values of P, for these values of P, we're going to have non-zero values of W, which means this is just a different way of saying that non-zero values of W exist, means that buckling has occurred. So this is very good. Now, we have to be a little bit careful here in noting that suppose we actually consider our beam cross section here like this, and let's say that this entire height is h and this width is b. So uh, we know that if you are considering the, let me just, so this is our beam, okay. So if you are considering the bending about an axis like this, okay, which is parallel to this top edge and this bottom edge, then the second moment of area is uh, 1 by 12 bh cube. However, if you are considering the bending or the second moment of area about this axis, okay, about this axis, then I is equal to uh, 1 by 12 h b cube. Now, if you look at this formula here, this I, it will depend on which kind of an axis you are taking this I about. Okay. Now, so depending on the values of B and H, now please do not be biased by this particular diagram. This is just a generic diagram. We could have B larger than H or H larger than B. So depending on those specific values, you have to see which I is smaller. Okay, the value that is smaller, it is that value which is going to predict the buckling first. Okay, because that is a smaller value. So it is like this, that you are keeping on increasing the value of P from 0. When it first hits the smallest value possible for buckling, then immediately buckling will occur. That's what the theory tells us. Okay, so from these two values, the one which is smaller, that will induce the buckling first. Okay, of course, yeah, you have to take the value of n equal to 1 also here. So let me see, with this knowledge, if I can draw some kind of a response diagram. So what I will do is, uh, so what another important thing, very classical uh, phrase that we often use is the critical buckling criteria, or the Euler buckling criteria. So what we say is that the Euler buckling load, so in honor of the Swiss mathematician Euler, Leonhard Euler, so this PE is uh, is given by this pi square EI, pi square EI by L square. Okay, so this particular combination is referred to as the Euler buckling load, PE, and you note that that is just the specific value obtained when n is equal to 1. Okay, so what we are going to do is we are going to uh, take this ratio P by E, PE, which is nothing but just n square, and then we are going to try to plot this out. So in the x-axis, we are going to have this P by PE, and in the y-axis, sorry about that, uh, we're going to take W. Okay, now you see, although uh, this is a very tempting thing to do, to plot W versus P by PE, but you note that there is a little bit of a problem here. You see, the solution that we have obtained, that is only just telling us about the critical values of P which will induce the buckling. But you see, we have still not obtained the specific value of B. Okay, so let me go back to the previous slide. You see, this B itself, that is still unknown. We have only predicted the possibilities of buckling occurring, but we still don't know the specific answer to our deflection, because until and unless we know the value of B, we do not know what W is. Okay, fine, that A cos x, Cx, D, they all vanish, but we are still left with W is equal to B sine kx. Okay, now uh, you can take different values of x. Now we know the value of k because we know this ratio P by EI, but we don't know what B is. So we really don't know what the amplitude of our deflection will be, even though we know that its nature should be sinusoidal like this. Now this is an important point to note when we are trying to draw our response diagram. You see, this P by P is nothing but n square. Okay, so if you take different values, okay, uh, so let's say, uh, so what we are basically doing here is that we are considering this n square values like 1, and this is 4. Sometimes what you can do is, instead of plotting this n square, what you can do is you can plot on this x-axis n, in which case these points will will be spread out like this. So 1 and then 4 and then at a larger distance 9 and so on and so forth. Anyway, so we have these things, but for W, all that you can do is to draw something like this with dot dot dot. Again at 4, it's dot dot dot. At 9, this is dot dot dot. So what this dot 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 means is that we really don't know what the amplitude of W will be. What will be the deflection of W? Okay, so maybe you can think of it. So some of you may argue that okay, we know W as a distribution of X. So where exactly, what value of W are we looking at? So maybe you can take the value at X equal to L by 2. Okay, so no problem, X equal to L by 2. So if you do that, you will get you have some idea that W is going to be non-zero. Okay, so it's like this. So this plot really is like this, that you're starting from n equal to 0. So it's like this until and unless you hit n equal to 1, it just flatlines like that. Okay, and then you have these things. And then the moment, what this theory is predicting is that the moment you make this n slightly larger than 1, again this theory is predicting that the buckling will not occur. So if you somehow manage to hit a load which is or suppose you apply a load which is larger than this value of 1, okay, if it is larger than pi square ei by L square but smaller than 4 pi square ei by L square, then this theory is predicting that it is not going to buckle. Now this particular thing, that it does not predict buckling for values intermediate between two such critical values, that is a little bit of a problem with this theory. It is one of the drawbacks of this theory that even though it is predicting buckling for a value pi square ei by L square, but for a slightly larger value it is predicting no buckling, which seems a little bit weird. Okay, and it is I mean, a problem with this theory. But within the confines of this theory, very theoretically speaking, you'll have the situation that when you hit the value 4 pi square ei by L square, or the value 4 times the Euler buckling load, again it will show a non-zero deflection, meaning that some buckling has occurred, and so on and so forth, if you keep on going like that. So there is room for improvement in this theory also, even though it has managed to improve on the previous theory that we were talking about, where the bending and the stretching were completely decoupled. This is the theory which has made an improvement on that, and it has enabled us to predict buckling or bend or some kind of compression induced bending as an instability. That is the good thing about this theory, but at the same time this response diagram tells us that there is an issue with this kind of non-zero predictions or non-predictions of buckling between the critical values. Okay, uh, so ideally what should have been the plot is something like this, that you start from a value less than 1, you obtain this thing. Okay, you obtain a non-zero value of this W, but if you keep on increasing the value of P by P, so if you go beyond this, it will still remain non-zero. Okay, the W will still remain non-zero, and if you keep on going like that, it will somehow go on like that. That would have been a proper theory. Okay, that would have been a proper theoretical prediction. Okay, so we'll see how we can try to improve this theory also, but that is for later. Okay, on that note, I'll end this video. Thank you very much.